Hello everyone. Thanks the organizer and my friend Katisak for inviting me to give a talk for the 50th anniversary of Quantum Thailand. I hope that my talk can give some introduction of some academic work of my group, and I will also introduce some activities and products of QKD products from China. Thanks very much. Now, the title of my talk is Progresses on Security and Attacking of Quantum Key Distribution. And I'm from the University of Science and Technology of China. In academic field, my major is to research the security and attacking of quantum key distribution. This is my content. First is the background. In the background, I will introduce what is QKD and its usage, and I will also introduce some products and activities from China. Then I will introduce some academic progresses on the security and attacking of quantum key distribution, mainly from the works of our group. So the first, let's go to the background. This is the background. Everyone knows that secure communications are very important for everyone in the world. For secure communications, there is a information sender called Alice, and information receiver called Bob. And Alice and this is Alice and Bob. And Alice want to transmit some plain text to Bob via some public channel. But there is an eavesdropper Eve. He may type the public channel. But for Alice, he want to his plain text is only known to Bob, and Eve cannot get the this message. But the channel is public, so how Alice can achieve his goal? So we know that the encryption and decryption is very important. This is also we know this is cryptography. Alice will prepare his plain text, then he encrypt his plain text with public key or private key. Then the encrypted message will be transferred in the channel. The Eve only gets the encrypted message. He may cannot know the plain what is the plain text. The encrypted message is unknown to him. He does not understand the encrypted message. But for Bob, he can decrypt the encrypted message. Then he gets the plain text. So Bob can get the what Alice want to send. So the encryption and decryption is mainly based on public key or private key algorithms. This is classical cryptography. And for public key, we know it is well known that the public key is RSA. The security of public key is based on computation complexity. This means that even if knows the public key, he cannot know the private key unless he has very powerful computational ability. So the security of a public key is based on computational complexity. And for private key, some private key algorithms such as AES is also based on computational complexity. So for this private key and or public key, they must ensure that EVE has limited power of computation. But we know if EVE is equipped with quantum computers, he may attack the public key or private key, and he may know the plain text. He may know the plain text. So this is not secure if EVE has very powerful ability of computation. But we know there is an algorithm for private keys called one-time pad. One-time pad encryption is the only one proved to be informational theoretical security. In the one-time pad, we assume that Alice and Bob has a very long random case. These truly random cases are only known to Alice and Bob. And Alice and Bob use this case to encrypt and decrypt the messages only with one-time pad. It means that when the keys are used, the keys will be disposed and never reused again. So this one-time pad is informational theoretical. It means that even if has quantum computers, he cannot attack one-time pad. So one-time pad is information theoretical security, also called unconditional security. But for the one-time pad, how can we get so many keys? So this is a problem. Fortunately, quantum key distribution can provide us a method for distributing secure keys between Alice and Bob. This is a well-known quantum key distribution or QKD protocol BB84. In BB84, Alice will prepare some quantum signals with diagonal polarization or horizontal polarization. There are 4 quantum states. Alice prepare for 4 quantum states randomly, depending on his k bit, and transfer the quantum signals to Bob, and Bob will detect the quantum signals with some quantum detections. In this protocol, Alice and Bob can share a secure keys via this insecure quantum channel. It has been proven that in this scheme, Eve cannot get the message of the Alice and Bob's key. So with QKD, Alice and Bob can share secure keys. Then with one-time pad, they can achieve their goal called unconditional security, unconditional secure communications. So BB84 or QKD is very powerful even when Eve has quantum computers, and it is a highly attractive solutions for secure communications in the age of quantum computers. So this is the background, and I will also introduce some QKD products and QKD activities in China. These are two typical QKD products. This is QKD terminal. This is QKD terminal with 50 megahertz replication rate, and this is advanced QKD terminal with 1 gigahertz repetition rate. So these are 2 products from China. QKD protocol from China. And this is architecture for the quantum key distribution network served for many applications in China. There are 3 layers of the QKD networks. The first layer or the bottom layer is key generation layer. In this layer, there are many QKD devices. Between the QKD devices, they can generate quantum keys. Just as mentioned by me as the BB84 protocol. Then the middle layer is management of quantum key. In this layer, there will be some service center to manage the quantum keys generated from the bottom layer. And the upper layer is applications layer. In this layer, there can be many applications that can use the quantum keys to encrypt their messages, like video conference, email, and also mobile phones can use the keys from the bottom layers. So this is a typical architecture for quantum key distribution networks. And this is an important QKD network in China. This is built by our group and QAskY. In this network, 3 cities in China are connected by QKD. They are city of Hefei, city of Wuhu, and Chaohu. There is a long quantum channel to connect the 3 cities. So many institutions in the 3 cities can share quantum keys in these QKD networks. And with this quantum keys, they can achieve unconditional secure communications. And this is another QKD application for a hospital at Beijing. In this hospital, we integrate quantum technology and classical cryptography to build a solution for the information security for a typical hospital. We use quantum key to protect the video files that must be in storage for many years. They are top secret, and we also employed quantum key management system to provide quantum key service. So this is a typical solution for QKD in a hospital. Actually, there are many other applications or activities of QKD in China, but for time, so I just tell these several examples. Now let's go to the academic contents of my talk. So from about mentioned BB84, it is theoretically unconditional secure that we know. But it's unconditional secure. We know that Bob must have a perfect detections. But in practice, we know QKD Bob's single photo detectors may be vulnerable and very complicated. So in sometimes its single photo detectors may be vulnerable to some unexpected imperfections. This may lead to some security risks. To address this issue, there is another important QKD protocol called the measurement device independent QKD protocols, also called MDI-QKD. So MDI-QKD, MDI-QKD, Alice and Bob both prepare some quantum states and transfer these quantum states to an untrusted middle station. This untrusted middle station can measure the quantum state and broadcast some messages. In this protocol, the security is not based on the how the middle station to measure the quantum state. So the security of this protocol does not rely on the how the measurement devices. So it is highly security when we consider that the security may be spoiled by the imperfections of measurement device. And the MDI protocol is very popular for in academic research. So we make some work focusing on this protocol. But in MDI protocol, Alice and Bob must prepare quantum states perfectly. This is maybe also quite questionable. This is because there are some photorefractive effects or laser damage or external magnetic effect or patterning effect that may disturb the preparation of quantum states. So the source side must be carefully considered in the MDI protocol. The source side loopholes are dangerous, so we must take care for this. So there we have some works focusing on the source side security. First is misaligned encoding. We know that in MDI protocol, the encoding must be idle, and that means pure states, indistinguishable bases, and no set channel and protected devices. But in practical encoding, this maybe cannot be met. Let's take an example. In an idle system, the source side, the signal of source side may be like this, so they can prepare quantum state perfectly. These are perfectly well quantum states, and 0, 1, plus, and minus. But in practical, we know the signal voltage may be not perfect like this. Then the quantum states become like this one. This is not perfect. There are some errors in these quantum states, but this is very possible in practice. So in this case, how to ensure the security? So we must give some method to overcome this problem. This is the density matrices we will use. And we use the Shor-Prinsky's formula to prove the security. So we propose a new protocol called the misalignment tolerant MDI protocol. In this protocol, the quantum state can be with errors. This is the sketch of our security proof, and this is maybe two mathematics. So let's go first. Then this is the simulation. From the simulation, we can see that our protocol can distribute a perfect security case for long distance and high K rate, even when the source side is vulnerable to some imperfections. And we also carried out an experiment. In this experiment, we carried out our protocol, and this is the result. We can see that from the experiment result, our result can fit the theoretical simulation results very well. So our next work is induced photofractive effect. We know that in MDI, the source side must be perfect, but this may be questionable. So let's take this. So in MDI, we must make sure that Alice and Bob can estimate the how many bits are not secure. So from how many bits are not secure, then they can make carry out the private amplification to make sure the final cases are secure. But if their Alice Bob's estimation is wrong, then it will be not secure. So there may be some attacks like this. They can that we call how to make this. They can use that the induced photorefractive effect. So what is induced photofractive effect to attack QKD system? Indeed, this is, we can call that in QKD the systems. There are some devices to modulate the intensity of laser. But if the intensity modulator are disturbed by some external lasers, it may not work well. So like this, there is some unexpected light shed on this intensity modulator, then there will be internal electric field. Then if you Alice Bob apply some voltage to this device, indeed, then the voltage of this device is not correct. So this makes the intensity modulation is wrong. Then with the wrong intensity modulation, Eve may attack the system successfully. This is our experiment. We can see that in imperfect situations, Alice and Bob should make sure that the intensity of their quantum states are this here, here, and here. But if there are some external laser here, then their intensity of quantum states may be like this. They will know this is totally wrong, and then Eve can with this external laser signals to make the senders works not perfectly, then they can attack the quantum system. So this is the attacking proposed by our group. And the last work is fully passive QKD. In most QKD protocols, and we must prepare quantum states actively. This means we use some phase modulators, intensity modulators to prepare quantum states actively. But we know for this active method, you must apply some voltage. But this voltage may be noisy, or there are some wrong signals. Then the quantum states you prepared may be not perfect. So this is not good. But for the fully passive QKD, the quantum states is not modulated actively, but the states are generated in a passive way. In this way, we can say like this figure. If we observe some measurement results, different measurement results correspond to different quantum states output here. So this is the idea of passive way to prepare quantum states. In a word, we can observe different measurement results in Alice's side to prepare different quantum states. So this is our experiment. So you can see that by observing the measurement result in Alice's way, Alice's lab, they can prepare different quantum states. This is another figure. And the quantum states prepared, the quantum state located here, and here. One can say that it is different from BB84. It's more complicated in some sense, but it is more secure since we do not prepare quantum states actively. So this is the experiment results. We can see that we can generate K in this loss. But of course, for fully passive QKD, its performance means that the fiber loss or K rate is not as good as BB84, but in some sense it is more secure. And at last, we also we also propose a fully passive MDI QKD protocol. This is our paper. And finally, there is a discussion. In this discussion, I would talk that source side security deserve more attention because MDI protocol has been a very popular protocol. So for the MDI-QKD protocol, we must take care of source side security. We may propose some new protocols that can tolerate more source side imperfections. And another is intensity modulator and tomography is important. We must make sure that the intensity modulator works correctly to prepare the correct intensity. And besides, bias-free IM is also important because bias-free IM will be free from the photorefractive attack. And finally, we must know that devices that are susceptible to EVE's interference should stay as far away from Alice's exit port as possible. So this is discussion of my talk. I think that QKD is very powerful, and anyway, it provides a way of unconditional secure for distributing a case between distant peers. Even when the eavesdropper has quantum computers, QKD can also make sure the security of the communication in principle. But we know that security, the unconditional security is in theory. If we consider in practice, the QKD may be not so secure because your devices may be questionable. Your devices for implementing QKD may be imperfect, and maybe there are some noise in your device. This makes you implement QKD protocol not very correctly. This opens some loopholes for Eve. So in the age of QKD, we also need consider security very carefully. But anyway, I think QKD is very good and offers very valuable way to protect the information security. As far as I know, QKD is the only way to be has been proved can beat quantum attack from quantum computers. And the PQC or some other classical algorithms are not proved that they can beat any quantum attacks. So this is my talk. Thanks for attention. Many thanks.